Okay, it is now 10 after, so welcome back everyone to MAT1841. Let me know if there are any technical issues with chat. So just if you're in chat, could you just put something in there to make sure things are still working right now? And let's go ahead and get started. So what did we do last time? Is there anyone in chat? Okay, well, anyway, let me know if things are going wrong. Yeah, so what did we do last time? We started talking about percolation theory. So the basic idea was, if you consider some infinite lattice and you have some random process that opens or closes edges or nodes in this infinite lattice, then you have some random graph model, and you can ask similar questions as we did to the Erdos-Renyi random graphs. Most importantly, is there a path from one side to the other? But now, of course, that's a little bit, that's not abstract enough. The real question that we're going to ask is there an infinite path in this graph? Because that will, if there is an infinite path, then there's probably a path from one side to the other, and so on. And we started going through this proof. And so we first proved that if the probability, so we're working with lattice percolation, and we first proved that if the probability of having an edge in your, be open in your lattice is less than 1/3, well then, no, with high likelihood there isn't an infinite path, because the probability of there being an infinite component at the origin, infinite size component at the origin was 0. And now we're trying to prove the same thing for p equal to 1/2. So we're trying to show that for p equal to 1/2, the probability that the origin is in an infinite size component is also equal to 0, which would show that the critical phase transition point is above 1/2, or greater than or equal to, not this 1/2. And the way we're going to do this is we're going to be making use of actual geometry. So in all the things we did previously, we didn't actually make use of geometry because there wasn't any. So an Erdos-Renyi random graph doesn't really have geometry because every node can be connected to every other node. And in our using the first moment method, or something like the first moment method for our previous theorem for p less than 1/3, we did basically the same. We also didn't make use of the geometry. Like this theorem here would have been true for, well, any any 4 regular graphs. So where all the nodes had 3 edges, or 4 edges, and you don't return back to the previous one. But now we are going to make use of geometry, and today's lecture is going to be a little bit technical, but basically the basic idea is that we are working in this dual graph to the original lattice. So you take your lattice, you translate it down by 1/2, 1/2, and then what ends up happening is the edges of this dual lattice correspond precisely to non-edges in your original lattice. And one of the things we showed is that if the origin is in an infinite component, that means it can't be surrounded by a cycle in the dual graph, because the dual graph is precisely the existence of non-edges. And this is something we could do because, and it turns out that there will be properties that of the dual graph and the graph itself that make them similar. The most notable being that they're both going to have probability equal to 1/2. And so they're going to be basically the same type of graph, just slightly different. And the proof sketch is we're going to consider the probability of having an open cycle in an annulus, and then we're going to keep on taking a bunch of bigger annuli, and then from that we're going to show that there is probability 1 that you have some open cycle containing in the dual graph containing the origin. Okay, so that was a quick review. Any questions about any of that before we go on? Okay, and I think the last lemma that we had but didn't prove, so we stated this, is if there is a rectangular k by L portion of the original lattice and a corresponding k plus 1 by L minus 1 portion of the dual lattice, so I've drawn those here in blue and green, then there exists either a horizontal path in R or an open horizontal path in R or an open vertical path in R prime. And it's really easy to show the opposite of that if there is an open horizontal path, then there can't be an open vertical path in the dual graph. But what we're trying to show here is existence. And the proof is almost entirely geometric. And basically what we're going to do is we're going to walk through a maze. What maze, you might ask? Well, this maze here. So let's draw out a copy of that and see what happens. And the maze I drew unfortunately goes across pages, which makes it a little bit more complicated, but hopefully we'll make it work. So let's go ahead and draw a maze as an illustration. So we have our, let's have our 4 points. 4x4 grid. It's actually n by n, but that takes a lot of time to draw. So, and our dual lattice here in green. Oh, and actually we're going to draw this slightly bigger because what we want is we want this one to be K by L. Oh, that's way too many of them. K by L. And we want this one to be K plus 1 by L minus 1. So this is exactly the structure we have here, except I'm drawing out individual points. And we have some number of edges between them. So let's see if I can get these edges correct. I mean, it doesn't really matter if I get them wrong. The same thing will still be true, but I drew one that I would sort of like to do. So let's see. Da, 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 da. And let's see. Da, 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 da. And let's see. Let's keep on going. And which one was there? So I think these are all green. Those are green, 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 green. Should really have just done this randomly. It's true for any one of these graphs, so it doesn't really matter that I'm doing it in a particular shape. Okay, I'm just going to do the rest of these edges randomly. Okay, I think I've put in all the edges there. Oh no, forgot all these. Okay, so this is one example of a graph and its dual graph. And you notice it looks sort of like one of those mazes you do in like elementary school, right? You could start at a particular point. Let's say we start at this point A. Actually, let me put this in a very specific spot. Start at this point A, and then maybe this is B, this is C, and this is D. So what I claim is that if you walk through this maze, you're going to, starting from A, you're going to end up at either B or C. Always. Can anyone see a proof of that? There's some invariant that is true if you just follow, if you like walk through this maze. Yep.
One side is like green.
Exactly. Yep. That's the invariant. And so you notice that if you start at A and you keep the original, which is in blue, you keep the original wall. And here we're just calling it the wall because the edges form a wall. We keep the original wall on the right and the dual wall on the left. Well, then you're walking through and you have to end at B or C. Walk through maze, have to end at B or C. B or C because of wall invariant. You can't end at D because the walls are on the wrong side. And it also can't end in the middle, right? Why can't it end in the middle? Exactly. Yep. So if if these were ending in the middle, then the lines would have to intersect in order to properly close it off. But then you'd have an edge that was both in the original and dual graph. Can't end in middle because would require original and dual edges to intersect, which is incorrect by construction.
What will be an example of ending in the middle?
There goes my pen. So for example, if I drew this here, then you could end in the middle, right? Because then you'd start here, you'd walk through, but then you'd hit that, and you couldn't go any further.
Oh, I see. Okay.
Yeah.
So it's just not ending at B or C somewhere in the.
Yeah. So you like what we're basically claiming is that you follow this through, you will end up exiting at B or C. You can't stop in the middle, and you can't end at D. And it's basically because of this wall invariant, and because you can't have the edges intersecting. But notice this walk is simultaneously a walk on both of the graphs, right? Simultaneously a walk on both R and R prime, because one wall is on one side and the other wall is on the other side. So this is equivalent to starting at one of the 2 points that it's going and just following along. And so, well, if you end at B, that equals a horizontal path, horizontal walk on R. Wait, did I get them backwards? I think I might have gotten them backwards here. Oops. And if you end at A, end at C, that's a vertical walk on R prime. I think I switched them. Vertical wall on, wait a moment, did I draw these correctly? Okay, well, I copied down the proof wrong. But anyway, so the point of this is just that there's either a horizontal or vertical walk in one or the other. I'll double check that later and just make sure. I switched around the notation a little bit from the source because I didn't like the fact that they were doing, when they say K by L, they mean width by height. And I prefer to use the notation that's a little bit more like a matrix, which is height by width. And so that's probably where I ended up messing this up. Okay. But now what we're going to do is that we're going to let probability sub P of H of R be the probability of a horizontal path in R. This is a little bit of an issue because all my notation here is wrong. Let me do it correctly as if this were correct, and hopefully this won't mess things up. So this is H of R prime is horizontal path in R prime, and the probability of 1 minus P V of R be the probability of a vertical path in R. Okay, well, this implies that the probability sub P of H of R prime plus the probability sub 1 minus P of V of R is equal to 1. But if we substitute in 1/2 for P, then that implies that this probability P is 1/2, that's equal to 1. So if R is an n by n plus 1 rectangle, then R prime is an n plus 1 by n rectangle, which implies that the probability 1/2 of H of R prime is equal to the probability 1/2 of V of R is equal to 1/2. Did that work out? I think I might have an off by 1 error. Okay, hopefully that works out. Oh yeah, because you're just plugging it in, and so they're both equal, and so then they both have to be equal to 1/2. Okay, and so now we're going to let S be an n by n square. Horizontal distance to travel is less than n plus 1 in R prime. So probability 1/2 of H of S is greater than or equal to 1/2 for all n. I think I do have an off by 1 error. We can go back and look at it later, but the basic idea is that if we have a rectangle, so if we have 2 rectangles, one of n plus 1 by n and the other by n plus 1, then because the dual graph and the original graph have the same probabilities, what that means is, and then you have a probability 1/2 of crossing one or the other. When you look at just an n by n square, when the probability of crossing that has to be at least 1/2 in either direction. So it doesn't really matter which direction you're going. Okay. And I apologize for the notational confusion here. But yeah, so this is where we make use of the fact that p equals 1/2 is special, is because we have our original graph and we have our dual graph, and they're basically the same, or rather they have the same distribution precisely when p is equal to 1/2, and you can make use of this duality, which is what we're doing, to show that you have some high probability of bounded above 1/2 of having, or sorry, at least 1/2 of having a path horizontally or a path vertically in a square. Okay, and so this brings us to a theorem. So this is going to be a theorem by Russo, Seymour, and Walsh. Welsh, I think I got the name wrong. And what we're going to do is, remember, our goal here is to prove that there is some path in this, some cycle in this annulus with high probability, right? But now, it's not enough to prove that there is some path in a single annulus with some probability, because then there's some chance that you don't have that. What you need to do is, well, you look at all these different annuli, and you look at all these different paths. And what you want to do is show that there are an infinite number of these paths, all with some fixed probability. But now, in order to do that, you can't have the probability that the path exists depend on the size of the path, right? So you need to find some way of showing that independent of the size of your annulus, the probability that there is a cycle is the same, or at least greater than some constant value. And so that's the proof strategy we're going to be using today. And this is a simplification of an argument by Russo, Seymour, and Welsh. So we're going to let h sub n kn be equal to h of r, where r is an n by kn rectangle. And then for all k, there exists some constant ck such that for all n, the probability of hn kn is greater than or equal to ck. Okay, so notice that this can depend on k, but not on n. So independent of n, if you have a rectangle of this shape, there is some positive probability greater than the constant of having a path across it. And in order to prove this, we're going to need a couple more definitions. So we're going to go back to probability theory and discuss the idea of an increasing function. So we're going to let the state space omega be equal to 0, 1j. So basically our state space is you have a bunch of independent events that either happen or they don't, which is exactly what's happening here. We have a bunch of independent edges and we're asking if they're open or closed. So there is a partial order on omega given by little omega is less than, with the funny coset sign, a partially ordered set sign, w prime, if wi is less than or equal to wi prime, go away, for all I in j. And what we're going to say is a function f from omega to the real numbers is increasing. Let me put that in a different color. Is increasing if omega is less than omega prime. I always find it difficult to draw that funny less than or equal to sign. If that implies that f of omega is less than or equal to f of omega prime. So in other words, an event is increasing if its indicator, and an event is increasing if its indicator function is increasing. So basically what we're saying is that this is the function that, and so an example of an increasing function would be the existence of a path, right? Because if you increase the number of edges in a graph, well, then from some number of existing edges, well, then clearly the probability of having some path across it is only going to increase. And this is true of a number of these graph properties. So like the probability of having a large component only increases when you add more edges. So note that, yeah, so that's basically what we're doing here. And this is theorem 6.2 in the reference for this. which is that if we let x be equal to xi, where I is taken from the state space, we let that be an independent random variable taking values 0 and 1. And we're going to let f and g be increasing functions. When it turns out that the expectation of f of x times g of x is greater than or equal to the expectation of f of x times the expectation of g of x. We're not going to prove this. You can look in the reference. There's a proof there. So see reference. The proof is long and complicated. I mean, it's not complicated. It's just long. It's just by direct computation. By direct computation, and induction. So the intuition behind this is, as I was saying, if a set of edges in a graph, if you have a set of edges in the graph and x and y are vertices, then the event that there is an open path between them is an increasing event. As you add more edges, the probability that there is a path between them can only increase, it can't decrease. And what we're saying is that if you have, and the way we're going to use this is we're going to say, if you have two different events, one is the existence of a vertical path and the other is the existence of a horizontal path, then they are correlated. So they are not independent events because there might be edges shared between them. But if you increase the probability of having a horizontal path by adding more edges, you're also you're not decreasing the probability of having a vertical path. Okay, so that's the sort of intuition of this. And we're going to make use of this quite a lot in our analysis because we're going to be taking advantage of the fact that, well, these vertical and horizontal paths, we're going to be making a lot of use of them, even when they intersect. Okay, so now proof of RSW. Note that this will not be tight, and you'll see what I mean by it not being tight very shortly. This is super not tight. Okay, so we're going to let F1 be the event that there's an open path connects the right side of 2n by 2n square with top and bottom of n by n square in lower left quadrant. Okay, so what are we doing? So we have some square. This is 2n by 2n, 2n by 2n. And we have some lower left quadrant here. So this is n by n. And what we want is we want to know the probability that there exists an open path that connects this, the right side of the 2 by n by 2n square with both the top and the bottom of the square. So, well, we know what the probability of having a connection between 2n by of a path across 2n by 2n is greater than or equal to 1/2. So this would be something like this, right? So probably it would be just having a horizontal edge going across. And we know that the probability is 1/2 of j of n is also greater than or equal to 1, is also greater than or equal to 1/2. So now what we're going to do is we're going to let G be an open vertical path in n by n lower left square. And we're going to let G prime be its reflection about y equal to n. So if G is, let's say, this thing, G prime is going to be, let's see if I can draw this, something like that. Does that look like a reflection? Sort of, close enough. So basically what we're doing is we're taking, for any particular open vertical path in the lower left square, there is some reflection about it in the other direction. It's not necessarily open, but there is some reflection of it, right? And now what we're going to do is we're going to let H, let's have this in red since I've already drawn it, be a horizontal path in 2n by 2n square. So by symmetry, it must cross either G or G prime with the same probability of crossing one or the other. Okay, so basically what we're saying is that this might cross this way, or it might cross this way, but it has the same probability of crossing either because it's a mirror image of each other, right? So because this entire thing is a mirror image, the chance that it crosses at the top or the bottom has to be the same. And so we only care about the probability when it crosses at the bottom because the G is the path that we care about. So therefore, we know that the probability of F1, I'm going to leave out these 1/2. So basically all these are dependent on P equals 1/2. I'm just going to stop writing them. Probability of F1 is greater than or equal to 1/2 because that's the same probability of Euler times the probability of J2n by 2n, because that is the red path here. So that's the red path times the probability of Jn by n, which is, which is the blue path here. So this is equal to 2, or greater than or equal to 2 to the minus 3. So what have we just shown? We have just shown that, well, if you have a 2n by 2n square, there's this weird sort of structure where you cross over from one side into the lower corner of the other side. And what we're going to now do is we're going to use this structure, this gadget, and piece together to allow us to connect together the different sides of rectangles. So let's let event F2 be equal to the probability that there's an open path, or sorry, not probability, but just the event that there's an open path across a 2n by 3n rectangle. Okay, so what does this look like? So this is 2 by 3. So this is 2n, this is 3n. That means we can divide it up into 2 squares. So we can break into 2 instances. This is of F1 coupled with an open path in lower n by n square. What do we mean by that? Well, so if we draw this out, clearly this thing here goes something like this, right? So this is connected to the top and bottom of this lower left square. But by symmetry, we also have another path that looks like that. So that was 2 instances. And we can connect them together with this open path. So there's some path like that. Therefore, the probability of F2 is greater than or equal to the probability of F1 squared times the probability of Jn by n, which is greater than or equal to 2 to the minus 7. So you can already start to see how this is very not tight, right? So the chance that there is an open path is probably actually a little bit higher than the numbers we're going to get because we're just taking these exponentially smaller lower bounds. But you'll notice that everything here is still invariant to n. So this is just any square that is, any rectangle that is 1.5 times as wide as it is tall. Okay, and we keep on going. So now you sort of see the strategy and you can sort of predict what we're going to do. We're going to now extend this out even more, right? Let's let event F3 be equal to open path across 4n by 2n rectangle. Okay, so that's going to be a bit painful for me to draw. That's all right. So we have a 4n by 2n rectangle. So it's twice as long as it is tall. And we're going to break it up into, well, 2 copies of our previous event. So the probability that of F3 is going to be greater than or equal to the probability of F2 squared. And that's going to be this event and this event. Oh, I drew it too far. And what else do we need? Yeah, we just need another vertical line. So this is these 2. And we just need a vertical line in this 2n by 2n square times probability of j of 2n by 2n, which is greater than or equal to 2 to the minus 15. Okay, and we just keep on going. So note that the important thing here is no actual dependencies. Dependencies on n. So we know that the probability of F3 is equal to the probability of j 4n by 2n is equal to the probability of j 2n by n. And now we have this 2 by 1 thing that makes it a lot easier, because then we just combine these over and over and over again with vertical lines connecting them together, and we're basically done. So we can combine process to get probability of j of kn by n, which is equal to ck for some constant, ck greater than 0, by just continuing this process and connecting them. In particular, the probability of j 3n by n is greater than or equal to 2 to the minus 31. Because, of course, this is 2 copies of 2 to the minus 15 plus a vertical thing to connect them together. And you just need more and more of these, but note that these are all constants, and they're all bounded away from 0. They're not bounded very far away from 0, but they are bounded away from 0. Okay, so now let's go back to the rectangular annulus. So let's go back to the rectangular annulus. And we're going to let FA be the probability that an open cycle exists in 3n by 3n annulus, not including center n by n. Okay, so let's draw this out. Well, clearly, probability of FA, does anyone want to guess what the probability of this one is? Yes, 3n by 3n.
Probability of j 3n times n squared times jn by n squared.
So there are a number of different constructions you could do, but let me give you a hint. Let's consider like this 3n by n thing, and this 3n by n thing, and this 3n by n thing, and this 3n by n thing. Yep, that's it. So it's just 2 to the minus 31 to the 4th, because you have some probability of having this path, you have some probability of having this path, some probability of having this path, and some probability of having this path. And yes, you could do other constructions. Obviously, once you have the 2n by n building block, you can do this arbitrarily as you please. But so this is one construction of it, and so this is equal to 2 to the minus 124, which is kind of small, but it's still independent of n. And that's all we care about. We just care about this being a constant value. It doesn't matter how small it is, so long as it's bounded away from 0 and doesn't like decrease with n. So no matter how big of an annulus you have, you're going to have at least a 2 to the minus 124 probability of having a cycle in that annulus. But now this is independent of n. So the key here is now we just surround the annulus with infinitely many larger annuli. And each of those has an independent probability of being, so let me draw out the first couple. So let's say we're going to start out small because we're going to run out of space. So this is one of our annuli. But then, of course, you can draw out the next bigger one. So it's scaled up by a factor of 3. I'm not going to draw the next one because then it's going to be scaled up by a factor of 9, right? And so we have some probability of having lat, and we have some probability of having list. And note that these are all actually independent. So we have some probability of having something out here as well. And so these all have independent probability. And so, well, note that the probability of no open cycle in annulus is less than or equal to 1 minus 2 to the minus 124, which isn't a great bound, but we have an infinite number of these annuli. And so the probability that no open cycle in K non-overlapping annuli is going to be less than or equal to 1 minus 2 to the minus 124 to the K. As K goes to infinity, the probability goes to 0. So almost surely there is an open cycle surrounding the origin. And note that this is true of both the original graph and the dual graph because they have the same distribution. And so almost certainly there is no infinite component that's 0 in in either graph, which then implies that theta of 1/2 is equal to 0, which implies that the transition probability is less than or equal to 1/2. Transition probability, the phase transition critical point, is less than or equal to 1/2. So there's another theorem, which, so note that this theorem here was proved in, did I write down when it was proved? I think it was 1960s, I want to say. Yeah, so this theorem by Harris was proved in 1960. There's another theorem, which you can look up if you want, by Keston. Hi, everyone. So I am inserting this into my video because it turns out I did actually get the direction of this inequality incorrect. So earlier in lecture, I said that it was less than or equal to 1/2. It's actually greater than or equal to 1/2 because, of course, if theta below p sub c, theta has to be equal to 0, and so we know showing that theta of 1/2 is equal to 0 implies that p sub c has to be greater than or equal to 1/2, not the other direction. So I'd like to thank my students who corrected me, and I apologize for the confusion. But hopefully for those of you watching on YouTube, this won't be an issue. Okay, so the answer is that in between these two theorems, well, obviously PC is actually equal to 1/2. And these sorts of transition points are things that people have calculated for a number of different lattices. And so you also have things like the triangular lattice. People have worked on that. You have hexagonal, different kinds of lattices, different kinds of shapes, as well as like node percolation instead of site percolation. And so as well as higher dimensions, that's something people often care about. So this is not actually useful for anything in the real world because we aren't, maybe not nothing in the real world, but normally our material scientists aren't creating 2D materials, at least traditionally. Maybe they are now. Actually, they almost certainly are now. But anyway, traditionally, like you would want something in the bulk, and so you'd be interested in these sorts of transition probabilities for 3 dimensions, usually. But people have done this for a while and have results for a number of these kinds of things. Okay, and that ends my section on percolation theory. We have a little bit more time, so let me just go ahead and introduce wavelets. I am unfortunately a little bit offset, and so my classes aren't beginning and ending on my lecture days, which is a little bit of an issue, but hopefully not too much of one. Oh, did anyone have any questions about percolation theory before we finish up with that? So basically just another cool application of random graph theory. Okay, so let's talk a little bit about wavelets. I will only have enough time to get through the basic introduction anyway before class has to end. So let's talk about orthonormal bases of the space of functions. Let's say we want an orthonormal basis on the vector space of functions. So what's the first such basis that you probably encountered in an analysis class? Yeah, so the Fourier series. So you probably encountered that in like a different differential equations class or something like that, or maybe a functional analysis class, depending on whether or not you took differential equations. So you have a Fourier series. So let's just f of x is equal to the sum over n to minus infinity to infinity of each of our components, and times some combination of sines and cosines, so e to the 2 pi I times n over t times x, for some function x that is in between minus, for some periodic function that's between t over 2 and t, and minus t over 2. Okay, so that's the standard Fourier series. And of course, you can generalize this to the Fourier transform. Did I spell that right? I mean, you can't tell if I spelled it right because you can't tell what my letters look like. I feel like my handwriting is particularly bad today. You should let me know if that's the case. So we have a Fourier transform, which is basically the same thing, but continuous. So we have a f hat of xi. I can't ever draw xi, so hopefully that's sufficient. From minus infinity to infinity of f of x. So it's just some integral from minus infinity to infinity of x times e to the minus 2 pi I x xi dx. And the opposite, which is just f of x is equal to the integral from minus infinity to infinity of f hat of xi e to the 2 pi I x xi d psi. So you guys probably saw this before. If you haven't, it's really cool and you should learn it. It's a lot more important than wavelets. I don't want to say it's a lot more important, but it is more important than wavelets. So you should learn that if you haven't yet. But for our purposes, there are some disadvantages of sines and cosines, which is basically what we have here. So, but sines and cosines are distributed in support. So like a sine goes everywhere, right? And so if you have some function that is 0 at most places and then does something here, sines and cosines are really bad at approximating this, because in order to do that, you need to somehow cancel out all these components with some other waves. And so that is the goal of wavelets, is to basically come up with an orthonormal basis set for the space of functions, but that is compact in support. And so, and ideally you want other properties, like you might want some amount of smoothness, you might not, but you want some other orthonormal set of, some other orthonormal basis that is finite in support. And that's where we get started with defining wavelets. And in order to do that, we're going to have to define a couple of things. And I think I have just enough time to define dilations. So a dilation is a mapping that scales all distances by the same factor. And a dilation equation, is an equation where a function is defined in terms of shifted scaled versions of itself. So let's give an example of that. So we'll give the very simplest example first. So let's say f of x, oh, actually, let's give the general form first, and I'll give a simple example. So this is the general form we'll be mostly working with. So it's sum from d equals 0 to d minus 1, ck f of 2 x minus k. So by which we have a scaling factor, which is this 2 here, and we have a shifting factor, which is this minus k here. And we have we have another scaling factor, which is the ck. So how tall are they? But it'll be a little bit more obvious when I give a couple of more concrete examples. So for example, we have f of x is equal to f of 2x plus f of 2x minus 1. Okay, so what we're saying is that this function has to be equal to itself, two copies of itself, one that's just shrunk by half, and the other that's shrunk by half and scaled over. And there is one very simple solution to this, which is just f of x is equal to 1 when 0 is less than or equal to x is less than or equal to 1, and 0 elsewhere. What does this look like? Well, if we draw this out, this is the function there. I'm going to draw these as boxes, even the just to make them look a little bit more wave-like, but obviously listing doesn't really exist there. And so what's going to happen is we're going to have two copies of that. So if that's f of x, then list here is f of 2x, right? And list here is f of 2x minus 1. So it's in shifted scaled versions of itself. And let's give a slightly more non-trivial example. Let's say f of x is equal to 1/2 f of 2x plus f of 2x minus 1 plus 1/2 f of 2x minus 2. And so let's give one solution to this. So basically what we're saying is that it's a copy of 3 scaled versions of itself, 2 of which are scaled down. Does anyone want to hazard a guess as to what the shape might look like? I'll give you a hint. There's 3 pieces. So
Yeah. Thing like 2.
yeah, so something like that. And yes, it does turn out to be a triangle. So yes, you're both correct, and we'll show you now. So it's going to, the function is going to look like x for 0 less than or equal to x less than 1, and minus x plus 1 for 1 less than or equal to x less than 2. Note that there are multiple solutions. So like you might have been thinking about a slightly different solution that also works. And 0 everywhere else. So what does this look like? So one solution. So this looks something like, let's say this is the 1, 1, 2. This looks like that. Okay. And so now we have several copies. So if you scale it, so the scaling along the x-axis is by 1/2, right? And so notice that here, we're also scaling along the y-axis by 1/2. And so our first thing is just going to be this piece here. Actually, I shouldn't fill it in because it'll get confusing. Okay, so this here is going to be 1/2 f of 2x. And notice that our final scaled factor, this thing here, also looks sort of like that. So we're also going to have a 1/2 f of 2x minus 2. That's going to be this thing here. And then we have this remaining stuff here, which doesn't really look like a triangle, right? But it turns out that like if you just like shift all this mass down, so if you think about taking this and just the pile of sand and you're dropping it down, then that actually ends up looking like this, which is precisely f of 2x minus 1. Because what we've done is we just taken the entire triangle and we shrunk it and put it in the middle. And if you add these things, 3 things together, you will find that these things add up to the original triangle. And so this is a slightly more non-trivial example of a dilation equation and one solution to the dilation equation. And it turns out that these are going to be the building blocks that we're going to use to create a new basis, and a new basis for the space of functions. And notice that these have slightly different properties. For example, this thing here is a tiny bit more smooth than this thing here, right? And so depending on what how you're constructing these things together, you can increase the smoothness of your basis vectors. Though we're mostly going to focus on building off a set of wavelets off of this dilation equation, since that's just the easiest to do. So that'll be called the Haar wavelets, and we will be starting on that next time. And I think class should end there. So thank you all very much, and I will see you. Yes, tomorrow. Today's Thursday. Yeah. Yep.
Thank you.
Yep. Thank you all for coming, and see you all tomorrow.